Recording in progress.
Ah, okay. If you're muted, it's
yeah.
logical. Okay, can you rest now?
Yeah, I guess now
I guess it should be
okay.
better.
Now it
But
should
again,
work.
maybe you can use that microphone, which is
But this one is better perhaps because it's.
Yes, you think so?
This morning it worked well.
For the discussion, maybe that.
And I'll share this one.
Thibault, can you hear us?
Yes, it's fine for me.
Okay.
Good.
Okay,
Good.
perfect.
There was not on my end, that's it.
Okay. And now, can you hear us again?
Yes, again.
Okay, good. Okay, thank you. So you can start? Yes.
Okay.
Okay, thank you. So welcome everyone. My name is Mathieu Speranzio. I'm professor at INSA Toulouse. BI. I have a chance to organize this presentation, this oral defense. So I'm going to introduce the jury members first. So with Arno van der Werf, researcher engineer in INRAE, in the laboratory called SAS, Soil Agro System in Rennes. Bernard Curec, director, so research director at INRAE, in the unity phare in Reims, actionnement agro-ressources et environnement. Thibault Lecomte, on the Zoom link, He's a maître de conférence in the University of Bretagne Sud in the laboratory called ERDL in ingénierie des matériaux, CMRS, Lorient. Myself, and obviously Ligia and Laurie, so Ligia is professor at INSA Toulouse, one of the supervisors, and Laurie is also a researcher at TBI in INSA Toulouse. Okay, so now you have about 45 minutes to present your work.
Okay.
And after that, we will discuss about it. The name of your PhD is quite long. Simultaneous carbon storage in marginal land and anthropogenic products for biopump, potential to induce negative emission and environmental mitigation.
Yes.
So that's a very good title, and I think it will be really interesting. So you have 45 minutes.
Cool.
Okay, and then we will discuss.
Okay.
Thank you.
Thank you. So good afternoon, everyone. Welcome to my defense. And today I'd like to present my thesis name with very long title. Okay, so let's come to the first part. As we all know, our planet is facing global warming now, and that's because there is more and more greenhouse gas in the atmosphere. And to coping with this problem, and many countries have announced their targets. For example, French government declared that we will achieve the carbon neutrality in the middle of this century. And as proposed in the Paris Agreement, we all human beings should strike together to limit the global temperature rise to well below 1.5 or maximum 2 degrees at the end of this century. To achieve these targets, we should lower the fossil carbon use involved in our society and in our economy. So we introduce you two approaches here. One is negative emission and the other is mitigation. So negative emission means that we biophysically remove the CO2 and other greenhouse gas from the atmosphere. It is a very important technology that could help us to limit the temperature rise to well below 1.5 degrees sufficiently. And for the mitigation, it means that through the developed technology, we could reduce the CO2 or other greenhouse gas emitted to the atmosphere. And the European Union has announced to reduce 40% of the greenhouse gas emission by 2030. And let's come to introduce you the main actor today, the biomass. The biomass play a critical role in limiting global warming since there is a lot of high amount of carbon storage inside. Plants could capture the CO2 through the photosynthesis from the atmosphere, while this captured carbon will back to the atmosphere through some activity, for example, like the respiration or residue decomposition. So the carbon here will not last for a long time. It depends on the rotation of the biomass. However, if we expand the value chain that we harvest the biomass and use the harvested biomass to manufacture the anthropogenic products, in this way, the carbon in the biomass is converted into the anthropogenic product, and that's all we call that carbon storage in the atmosphere. Of course, this carbon storage is not permanent. It's the carbon in the atmosphere will finally back to the atmosphere at the end of the product lifetime. So it's more like a temporal storage or like a delay emission. So you may ask, while if this system really help us in climate change or not, what if we absorbed 1 kilogram of CO2 today, but we emitted 2 kilograms or more tomorrow? So we need an approach to analyze this system. And LCA, the life cycle assessment, is a very powerful tool and widely used in analyzing the climate change and other environmental impacts. The other important carbon pool I'd like to introduce you today is the soil. Well, in fact, there is more carbon in the soil than carbon in the atmosphere. Here today, because since we consider more stuff involved with biomass, so we focus on the soil organic carbon, which we call SOC in short. So some plants could convert part of captured CO2 into the soil during the cultivation, so the level of the SOC will increase. In this way, we say that the carbon is stocked in the soil. And of course, if we want to apply this system, we will demand more land. And in this way, the conversion from the initial land use to the cultivation of biomass should be considered, as the land use change effect is very important because a lot of CO2 or GHG will be emitted through this way. So in conclusion, our thesis aim to store carbon in arable land and anthropogenic products at the same time. So that's we call our concept as CSAAP. So the arable land means stock carbon in the soil, and anthropogenic products mean stock carbon in the atmosphere. So there are three main processes in my thesis. The first part is to simulate the stock change during the biomass cultivation. So in this way, we could estimate the carbon storage in the soil. And then we use the LCA to analyze system to estimate the carbon storage in the atmosphere. And of course, since we will need more land, our territorial range is in France, and the initial vegetation originally grown on this converted land should be included to estimate the effect of the land use change. And the final step is to estimate the whole system, the behavior of this whole system in the future, to know whether this system could really help us to achieve the different climate targets in different time points. So to whom have read my thesis, I'd like to introduce you the relationship between the thesis and this presentation. So this presentation has four main parts, and there are 7 chapters in my thesis. So the first 2 chapters consist by the literature review, where I got this idea and found some scientific gap in estimating the biomass system. And the second part linked to the chapter 3, where we propose a concept named the biopump. So we will explain you what is biopump here, and we'll investigate whether generically investigated whether this concept will really help us be meaningful to achieve the different climate targets. And for the third part, including chapter 4, 5, and 6, so consists by 2 detailed biopump case studies and to analyze some sub-questions, for example, which parameter plays key role in this strategy, and is there a major trade-off in other environmental impacts where we benefit the climate change but generate more pollutant to, for example, to the water or to the soil. And for the 2 approaches I mentioned before, the mitigation and negative emission, which the contribution of these 2 approaches is, which is the contribution of these 2 approaches in the strategy. And finally, we'll come to the conclusion and perspective part. So let's come to the second part. As you see, as I mentioned, that our thesis aim to store the carbon in arable land and anthropogenic product together. So what we call biopump is the way that how we apply the CSAAP concept. Biopump is a kind of plant that could increase the stock level during the cultivation, so stock the carbon in the soil. And after harvesting, the harvested biomass could be used to produce anthropogenic products, so stock the carbon in the atmosphere. Okay, since we explain you what is the biopump, then we'd like to propose some candidate plants that could be regarded as biopump and investigate the anthropogenic products to have a look which is the good carrier of the carbon in the atmosphere. And then we are identifying the potential land that's suitable for growing biopump and demonstrating our concept will really help us or not. So let's come, according to the literature review and these 5 major criteria, so we're selecting our candidates. The primary criteria is the stock change, since we want to stock the carbon in the soil. So at least during the cultivation, the plant should be able to increase the stock level. And for the yield, that's because whatever the plant it is, almost 50% of the dry biomass is consisted by the carbon. So if the yield is low, it means that it does not absorb a lot of CO2 from the atmosphere. And in another word, the mitigation, negative emission does not perform very well. And for the agricultural intensity, that's because our biopump might be planted on the marginal land or something, so we might not be able to give it a lot of careful agricultural management. So it will be very ideal if they could tolerate virus of environments. And for the suitability to grow in France and invasion rates, because our target area is France, so at least this plant should be able to live in France without bringing any invention problem. And then for each criteria, we'll assign point from 0 to 3. 0 is the worst and 3 is the best. So we'll assign this score to each candidate and rank them into the woody plant and herbaceous plant. So you can see that black locust ranked on the top of the woody plant, and for the Herbaceous plants, switchgrass, and hemp, but hemp is kind of annual grass, and then miscanthus as well, kind of in the middle of the rank. Further, we estimated the anthropogenic product with different lifespan based on these biopump candidates. So if we use biopump to generate something like the bioenergy, disposal plastic, or food supplement, they are consumed very fast. So the carbon in the storage, the technosphere will not be stored for a long time. They are not very ideal carbon carrier. While if we look for the textile, which is mainly made from the fiber of the plant, and we could get longer lifetime from 2 to 5 years. But if we use biopump into the constructor, we could get the anthropogenic products with much longer lifespan and up to 100 years. So the third step is to identify is there any potential land suitable for growing biopump in France. So according to the land data center, we looked at 23 land types in France. So first, we don't want to disturb the existing human activity. So we remove the land type linked to something like a road or urban. And then we will remove the land type that's obviously not suitable for growing biopump, for example, water, glacier, snow. And for the rest, our criteria is not to compete with food security. So finally, we choose rapeseed, intensive grassland, woody moorland, and natural grassland as the potential land. And you may be curious that why rapeseed is chosen, isn't it used for food? That's because in general, in Europe, almost 50% of rapeseed oil is used for the bioenergy instead of the food. So as we just estimated, the bioenergy is not a very good carbon carrier in the troposphere. So we think if we could improve its performance in the aspect of the climate change, and further, even if we continue to provide the same function, can we expand the carbon storage in the soil? So that's why we choose rapeseed. And for the intensive grassland, from the description of the land type used, it's hard to judge that it could be used or not. It's covered by dense grass, but not in the rotation. While in fact, the available area of the intensive grassland is very large. So we think that if we could include part of them, we will have much more potential land for growing biopump. So we think, of course, we don't know the exact extension, maybe 0%, maybe 100%, but at least a part of them could be used. And for the woody moorland and natural grassland, they are kind of abandoned, like idle land, but they are able to support biomass growing. So that's why they are chosen as the CV land. CV land is the short term of the carbon vulnerable land, and you may be curious that why we call our marginal land as the carbon vulnerable land. That's because we want to stock the carbon in the soil. So the initial stock level should not be too high, or otherwise the potential will be squeezed. So we look at the stock level of the France, and in France, if the stock level is higher than 60 tons per hectare, it's defined as high. So at first, we look the initial stock level with this 4 land type lower than 40 tons per hectare, and we could see that we did not find a lot of available results. And then we expand our boundary a little bit to 40 to 50 tons per hectare, and we got satisfied results. So finally, our criteria is to looking for these 4 kinds of land type with the initial stock level or lower than 50 tons per hectare, and to the maximum, we could get more than 24,000 square kilometers land available for growing biopump. And the final step is to demonstrate that our concept will really help us in climate change or not. So we track the carbon flow and use the miscanthus, if you still remember, because miscanthus ranked on the middle of the ranking. So we think it could represent the general performance of the biopump. And here the arrow on the left means there is some carbon absorption, for example, carbon capture through the photosynthesis. And here the arrow on the right means carbon emission, for example, the carbon emitted during the residue decomposition. And here we analyze 3 scenarios with very different lifetime. So the first scenario, the anthropogenic with very long lifetime, for example, 100 years using the structure. And the second scenario, anthropogenic with very low short lifetime, for example, the biofuel lower than 1 year. And the third scenario is between these 2 scenarios. So further, you could see that here is the carbon carbon stock and carbon consumed, so carbon flows change every year. And on the right is the GMTC, the global warming temperature change. It's an indicator for the global temperature. If the value of the GMTC is positive, it means that we increase the global temperature. If it's negative, it means we decrease the temperature. And also the legend on the upper right is the same for these two figures. You could see that even the carbon in the technosphere will be emitted back in very short time, as 1 year, there is still some carbon storage in the soil. So we can see that the GMTC is negative at the first. However, with the time goes by, there is less and less carbon storage in the soil. So at the year 2080, the green one with very short lifetime, and the GMTC finally goes positive. And while for the red one, because carbon is accumulated in the technosphere continuously, so the GMTC is decreased continuously negative, and the magnitude is larger than the green one, than the carbon in the soil. And the blue one is in the middle of these two scenarios. So from this analysis, we could say that our concept really help us in the climate change. While in this case, the lifespan of the anthropogenic products and the time points of our climate targets is very important. So let's come to the case study part. Here, according to our proposed rank, we choose hemp and black locust as our two case study. So hemp is kind of annual grassland, which with very good fiber in the straw. It's light and strong. So normally we cultivate the hemp to harvest the straw to get fiber. However, in fact, the seed of the hemp has 4 or 5 more expensive than the straw in the same unit. So in the first scenario, we are thinking what will happen if we only harvest the hemp seed but leave the straw on the ear. So in this way, we could maximize the carbon storage in the soil. So that's why we call our scenario, first scenario as SL in the straw left. And for the other two scenarios, we harvest the straw and use them to produce insulation board and the car panel with different lifespans. So we call it the scenario EB and CP. Well, the agriculture management for the hemp is kind of easier compared to the black locust because hemp is annual plant, so we assume every year they are same. But for the black locust, 10 years after the seedling, we'll conduct the first selective thinning, which means we cut some of the stem to provide the better situation, growing situation. For example, more sunshine, more nutrition for the left stem to grow. And similar, 10 years after the first thinning, we'll conduct the second selective thinning, and with pruning. Pruning means that we cut the excessive branch. And after that, the whole rotation from seedling to harvesting, finally mature and harvesting, the rotation for the black locust is 35 years. And the harvested biomass will be used to produce cross-laminated timber, the CLT, and medium density fiberboard, the MDF, with different lifespan. And it should be noticed that at the end of life of the CLT, part of them will be recycled and to produce the MDF. Well, for the initial vegetation that originally grow on the CB land, they will be calculated as a reference for both two case studies. Okay, so to estimate the performance of biopump, the first step is to simulate the plant growth. For the hemp, again, it's an annual plant, so we assume the yield is same every year. So we just know the yield of the seed and straw, so we could calculate the above ground biomass and the below ground biomass based on the different proportions. While for the black locust, it's a little bit complicated because the biomass of the groundwood is different every year, depends on the different growth rate. But similar for the other parts, they are also calculated according to different proportions to the groundwood. And the next step is to simulate the soil change to know how much carbon is stored in the soil during the cultivation. Here we use the AMG model and CTOL to conduct that. So the MG model is specially calibrated for France, so that's why we choose this for the hemp case. And for the CTOR, that's because MG model is not suitable for estimating the perennial plants. It will assume that all residue will decompose in 1 year, which is not true for the black locust. So that's why we use CTOR to simulate black locust. And when we come to compare the hemp and black locust together, we also use CTOR to harmonize them in the same framework. And for the input data, for the meteorology data, we get them from the DKIAs that were especially predicted for France under the situation SP 4.5. And for the soil characteristic, we get them from the FAO database. Exactly where we got the identified the CV land, while for the CN ratio, it's a kind of characteristic, but it's not included in the FAO database. So we search them from the literature review, and we try 3 CN ratio, 11, 17, and 12 in the MG model, and only 11 in the CTOR. And then after we get that, we'll use them to build the inventory and calculate the static and the dynamic LCA. So both static and dynamic LCA, we model the scenario in the consequential thinking. For the scenario SL of the hemp case, the harvested hemp seed will be used to produce hemp oil and hemp meal, which will be consumed in very short time. And for the two straw harvested case, so the harvest straw will be separated to fiber and sheaves and byproduct. So the harvested fiber will be used to produce the insulation board and panel respectively. And for the sheaves as byproduct, it will be used to produce hemp concrete for those two scenarios. And since we want to analyze the consequence of the biomass cultivation, so the process in the dashed line means this process is avoided, so it's kind of mitigated effect. And for the black locust, it's similar that will produce the CLT and MDF, the cross-laminated timber and medium density fiber board, and we will avoid the corresponding product. But for the initial vegetation, according to the map that we just identified, 20% of the initial vegetation is natural grassland, and 70% is woody moorland, and 53% intensive grassland, 20% rapeseed. And according to the land use description, we use heatherland to represent natural grass and woody moorland, and ryegrass for the intensive grassland, and rapeseed for the rapeseed land. We calculated the initial vegetation. We calculate it individually when we compare to the black locust scenario, while it is put as a negative input to merge with 3 hemp cases. And for the functional unit for the hemp case, because hemp is annual plant, so we assume every year they're similar. That's why we choose a functional unit as the what happened in 1 hectare CV land and in 1 year. For the black locust, we take the time as 1 rotation. So it's what's happened in 1 hectare CV land for 35 years. And since we consider the carbon capture from the atmosphere through the photosynthesis, so we'll consider this part of the carbon will finally back to the atmosphere at the end of the product lifetime to be balanced. And then for the dynamic analysis, both hemp and the black locust will be cultivated at the year 2022. So and will be cultivated continuously at around 100 years to cover the longest climate targets. And the final GHG flow involved with the hemp system will stop at the year 2262. So it's totally around 240 years. And for the black locust, it will stop at the year 2290. And we use the climate change impact tool with the matrix global mean temperature change, the GMTC united in Kelvin to estimate our dynamic results. Okay, so let's come to the result part. If you notice the icon here on the upper right, you will see that if the icon will indicate the result is only for hemp or black locust or both hemp and black locust. Here is the result of the hemp only for the stock change during the hemp cultivation. So you may notice that with all these scenarios, when the CN ratio is higher, so will get higher sock results. That's because higher CN ratio will indicate to lower the mineralization effect, so lower the carbon emitted from the soil to the atmosphere. And in this way, the sock level will increase. Further, in these six scenarios, only on the scenario that hemp straw is harvested and CN ratio is 11, hemp will decrease the sock. On all 5 scenarios, hemp could increase the sock. And then we choose the CN ratio in the middle for 17 to estimate its change during the initial vegetation growth. You could see that the initial vegetation is determined by the rapeseed and intensive grassland. For the rapeseed, it's because we only harvest the seed and leave the stalk on the field. So it's more like a hemp straw left case. And for the rapeseed, that's also for the intensive grassland, for the ryegrass, it's because it has stronger roots than hemp, so the carbon from the below ground plants is larger than the hemp. And for the average of the initial vegetation, it's between the 2 hemp cases, so between the straw left or straw is harvested. And scenario for the black locust differ a lot to the hemp. The sock change waiving according to the agricultural management. And so where there is the first selective thinning or harvesting, means there is logging, so there will be a huge amount of carbon input to the soil. Then that's why the sock will increase instantly. While this increase the sock will decrease, although very fast at the first several years, because the decomposition act is most active in the first several years. Well, another thing is that if we stop the time here at the end of the first rotation, you could see that the increased sock is almost 80%, then the increased sock at the end of the cultivation after 3 rotations. So it means that to be efficient to stock the carbon in the soil, we don't need to continuously grow the black locust for several long years for 3 rotations. We just need 1 rotation, that's enough. And for this high amount of the sock increase at the end of cultivation, it will not last for long years. After 50 years of the cultivation, if we do nothing, the sock level will back to the initial value. And if we merge the black locust and hemp together, you will see the carbon stored in the soil. The rank is black locust, hemp straw left, initial vegetation, and hemp straw harvested. And similar to the black locust, if for the hemp cultivation, if we stock the time here after 35 years, so the increased stock in the hemp case will be 80% of increased stock at the end of the cultivation. So similar, if we want to use hemp to stock carbon in the soil, we don't need to cultivate the soil such a long time. Well, though the black locust could stock more carbon in the soil, we also need to consider about the time points because at the very beginning, black locust is decreasing the stock and even lower than the blue one, lower than the hemp straw harvest scenario. So we need to consider about the time points we consider. And then we come to the climate change results with the static LCA. So normally for all blocks above the 0 axis, that means there is some GHG emission. And for the all blocks below the 0 axis, it means there is some GHG capture or this process is avoided. So if the net result is positive, it means this scenario damages climate change. And if the net score is negative, it means that we benefit the climate change. So we could see that in the scenario SL, though it could stock a lot of carbon in the soil. That's why you could see the length of the block or the carbon capture during cultivation is longer than the block of the carbon emitted during the residue decomposition. While, however, because of the emission from the land use change, it is still scoring positively, so it will damage the climate change. While for the other 2 scenarios, when we harvest the straw, though we have more emission during the product disposal and because of the manufacturing, but the emission during the residue decomposition is much lower than SL. That's because most of straw is harvested and used in the technosphere, not on the ground. And thanks to the avoided product, so these two scenarios finally score negatively. It means it can benefit climate change. And you may be curious that's why the reference flow is, when we estimate it individually, is negative, but it's positive here. So that's because we merge this reference flow as the negative emission in 3 HAMP scenarios. So it's like negative, negative, and it becomes positive. And for the black locust, it's similar to the HAMP. So the major positive block come from the product disposal and the manufacturing and the carbon emission during the residue decomposition, while for the negative block, they come from the cultivation, carbon absorbed during the cultivation, and the avoided product. So, but from the other environmental impacts of the HAMP case, we will see now that the land use change is not always a bad thing. For example, here, because the cultivation of the hemp will avoid the cultivation of the initial vegetation. So we also avoid the zinc emission to the soil because of the soil erosion during the ryegrass cultivation. And that's why even the scenario SLL score negatively here will benefit the non-cancer human health. And for the marine eutrophication, similar, though the most positive block comes from the hemp cultivation because of the nitrogen fertilizer use. But we could avoid more fertilizer use because from the initial vegetation, and that's why the SL is still scored negatively. And this advantage could be expanded by the avoided product in the scenario EB and CP. Well, in the freshwater eutrophication, because of the phosphate fertilizer use in the hemp cultivation, so the scenario SL score positively will damage this impact. But for EB and CP, because of the avoided products, provide some sort of mitigation effect. So these two scenarios finally score negatively still. And for the hemp case in other environmental impacts, you could see that it's much simpler because in most impacts, the negative part is provided by the avoided products, and especially from the avoided plastic board. Well, in the mineral and metal resource use, this avoided score is not be able to compensate the emission during the manufacturing because of the resin use. But here, the black locust is still, though the score is positive, but it's still lower than the reference flow. So it means the conversion will still benefit in this impact. But in the ionization, radiation, land use, and freshwater eutrophication, the score of black locust is not only positive, but also higher than the reference flow. So it means that the conversion to the black locust cultivation will damage these three scenarios, 3 impacts. And also it tells us that the avoided products is not always bring us the negative score. For example, here, that's because we avoided the disposal of plastic balls, so we avoided incineration and further avoided the heat generated during the incineration, and that's why we need to produce more heat to compensate this kind of heat loss. And if we harmonize the hemp and black locust in the same scenario, so we could compare their impacts together. In the aspect of the climate change, use black locust is much better than the hemp to get lower result. Well, as we could see that though most two biopump is negative in the impacts, in the environmental impacts, it means that it could benefit these impacts, but in some impacts, it's still positive. For example, in the land use, both hemp and black locust score positively. It means it will damage these impacts. And further, if you notice that the arrow bar here, because we did an uncertainty analysis, so in the non-cancer human health effects and the terrestrial eutrophication, it's hard for us to conclude that which scenario is better. But consider all environmental impacts. it's hard to say black locust and hemp, which one is better better black biopump, because black locust will score better in this almost 11 impacts, but hemp will score better in these 5 impacts. And then we evaluated the mitigation effects. So the mitigation effect, we found that there is kind of relationship between mitigation and the final net result. In these 5 impacts that hemp, the scenario CP scored most negatively, it also has the largest mitigation effects. So here we come to the dynamic part. Here we have 2 kinds of flow. One is bioflow and the other is non-bioflow. So bioflow means all GHG flow that directly involved with the biopump case. So we use this to represent the negative emission. And you could see that here at the very beginning, the bioflow, the negative emission are always decreasing. The GMTC are always decreasing because of the carbon capture during the cultivation, while at the end of cultivation, because for the hemp, most of the carbon is storage in the technosphere, so you can see net emission is kind of stable after cultivation, while for the black locust, most of the carbon in the anthropogenic products at the end of life, the disposal is incineration. So the carbon in this product will emitted back to the air in a short time. So you could see that GMTC continuing growth increasing at the end of lifetime. And if we look at the scenario SL at the beginning, it's always positive the bioflow. That's because the product in this scenario is only hemp oil and hemp meal, and we see they are not very ideal carbon carrier. So the carbon in these 2 products will be emitted back to the atmosphere in a very short time. And further, except the CO2, there are more GHG emitted, like with higher climate change factor than CO2, for example, Mason and 2O. So that's why it's positive at the beginning. Well, because, for example, the Mason has shorter lifetime than CO2, much shorter. So at the end of the cultivation, the bioflow is decreasing, and finally at the year 2157, the bioflow is negative, so it's finally become a negative emission again. And for the non-bioflow, as we just say, that the result is determined by the mitigation effect. So we use mitigation effect to represent, or we use non-bioflow to represent the mitigation effect. Here you could see that the mitigation effect sometimes is lower than negative emission, sometimes it's a lot higher than the negative emission. But in the hemp case, they are still kind of in the same magnitude compared to the black locust. The black locust, you can see that it's obviously determined by the mitigation process. And for compare hemp and to black locust, although black locust could provide lower GMTC, decrease more temperature, but we also need to consider the time point, since the black locust were not better than hemp before the year 2042, and it's even positive at the beginning. But for both hemp and black locust, consider the time targets that we can say that before. For example, the middle of this century and the end of this century and the end of the time boundary, they are not all, the GMTC are all negative, so both of them could help us in mitigating climate change. And finally, if we conclude all the results to have a conclusion to compare that. So for the soft part, black locust could store most of the carbon in the soil. It has the largest carbon storage in the soil, and it could capture more carbon during the cultivation. But it does not mean that they could stock more carbon at the end of lifetime scenario. EB, the hemp case, could stock more carbon than black locust, and more carbon because of the more carbon in the technosphere. Well, the larger negative emission also does not mean you can get the more negative net result in climate change, because it is determined by the mitigation so black locust is better. And here, if we consider that dynamically, as we say that the black locust will capture more CO2 than the hemp during the cultivation. So at the beginning, the negative emission of the black locust is higher than the hemp, while with the time goes by, at the end of the time boundary, hemp can stock more carbon, have larger negative emission than the black locust. And you could see that carbon storage at the beginning during the cultivation, black locust is higher, and gradually it comes to the hemp to the technosphere part. Okay, let's come to the conclusion. So in this thesis, we propose our concept of the CSAP and biopump to alleviate the climate change, and we identify there is potential land suitable for growing biopump, that's what we call CV land, and we analyze 2 case studies to answer the question that we posed before. So now I can tell you that yes, biopump strategy works for us in elevated climate change, and will help the France to achieve the carbon neutrality by 2050 and other climate targets, for example, to limit the temperature rise at the end of this century. And during this process, the parameter, for example, like the rotation of the biomass, the lifespan of the anthropogenic products, the disposal way of products are really important. And since except the scenario that we leave the hemp straw on the field, both black locust and hemp could help us in benefiting the climate change. And but there is some trade-off in other environmental impacts. For example, like in the land use, both hemp and black locust will damage this impact. And for the mitigation and negative emission, both these 2 functions are very important in this strategy. But in the hemp, negative emission and mitigation are kind of in the same magnitude, but in the black locust, the mitigation will respond to a higher temperature decrease. And further, here we only consider about black locust and hemp for our biopump. So if we have more time, we analyze more biopump into the biopump database. For example, here, because we analyze the hemp and cultivate that for 100 years continuously, which may be not so realistic. We will not do that. The hemp will be cultivated on March or May and harvested in the August or September. So it's like half year in space. So if we have more biopump in the database, so we could use them in the rotation to make our scenarios more realistic. And similar to the products, because here we only have 2 or 3 products for each scenario. So it is not totally not enough. There are various of applies of biopump, so we could investigate more. And further, we investigated these products in the aspect of the climate change. Well, however, maybe some products, they do not have so much high value in the climate change, but they will bring more profit in the economic aspect. So people will be more motivated to produce this kind of product, and it's also very interesting. And if you notice that for the dynamic part, we only focus on climate change. So in the future, if there is well-accepted methods, we'd like to use that to analyze the trade-offs in the future. And finally, an on-site experiment with the local condition will be very interesting to verify the estimation I proposed today. So at the end of the presentation, I'd like to thank you to remember help me to revising my thesis and coming to my defense. And of course, the warmest applause belongs to my supervisors, Eva Bahana and Ohiaman. It's you to raise me up, to step by step guide me to finish this PhD. And I'd like to say thank you to all the Cambridge Scopro and my colleagues in Team 10, Team 7, and all the TBI. We live together every day. We discuss the scientific problem, and you guide me, really help me in not only in the scientific field, but also in the daily life. Really say thank you. And I'd like to also say thank you to all my friends come here and online. It's you to make my life splendid here where I'm 500 miles away from home. So, and finally, I'd like to say thank you to Chinese government for providing the financial support to bring me here. and I'm very welcome for your questions. Thank you.
Thank you, Zhou, for this very nice presentation. So,
s'il y a des gens qui veulent partir, c'est le moment.
vas-y.
But keep it sharing. Yeah, you keep like that, and then you can have your.
I switch on the microphone. Maybe Thibault, you can hear me now.
Yes, it's fine now.
Switch
So
on
the
the
same
microphone.
problem as before.
Do you want to open your video, Thibault? Si tu veux qu'on te voit. Ok, ça a l'air de marcher. Okay, good. So now time for discussion. And we will start with Ayo van der Werf. Please, Ayo.
Okay, thank you. So thank you very much for your presentation. I thought it was very a nice presentation, very clear. Good job. And I think overall the whole thesis reflects a large amount of work and interesting results. To tackle your research questions, you have mobilized competences in environmental assessment and in soil carbon modeling. And I think that together with your directors, you have tackled a very important question. So the thesis is the result of an important and well-documented research effort. And in reading it, I must say, learned a great deal about the value of dynamic LCA and also of the implementation of global mean temperature change. So, well, that is very good. But you know that my job is also to go a bit further than this. So I think the strength of this work is in the formulation of the concepts of biopump plants and the exploration of the potential contribution of carbon sequestration in soil and plant products to reduce climate change. You use the dynamic LCA, consequential LCA, and global mean temperature change to clearly quantify the potential of these approaches. Now, and I appreciated much the use of a sensitivity analysis and uncertainty analysis to further strengthen the results. So overall, I think it's an important contribution to the environmental assessment of scenarios for carbon sequestration in soils and products. I missed a general discussion in which the results that you obtained are considered in a wider perspective. Of course, a doctoral candidate studies specific research questions, but also should have a wider view of the scientific and social context of the work. Now, I know that, well, in a thesis, time is always short, and maybe time was a bit short for this overall view. Also, I have some comments on, I think on the LCA side, the thesis is very strong, clear. For the modeling of biological systems, I think there were some lacks of agronomic and ecological understanding. For instance, as I mentioned in my report, rapeseed and hemp are not grown continuously. Hemp, you can do more or less. Rapeseed is completely impossible. And for instance, natural grassland, to consider that natural grassland consists of heather is kind of a shortcut. And also, I would have liked to see a more profound analysis of the discrepancy of the results of the C2 and the AMG model. So that being said, I have a few questions for you. So first, a more general question. In your introduction, you explained that climate change is a very major environmental challenge. Can you tell me what is another major environmental challenge?
Yes, well, because for us, we focus on climate change, so we say that it's a major challenge, but also there are very important stuff, for example, the loss of the biodiversity, and we also do, that's why we also do the whole life cycle assessment, because we not only have the climate change, we also have other impacts in other environmental impacts. So, for example, we see that both black locusts and hemp will damage the land use, and sometimes in the eutrophication, whether in marine eutrophication or freshwater eutrophication. So they all need to be included. So whether we not only consider about the climate change, we are benefiting that, but we also think about trade-offs. We don't want to damage other impacts.
Okay, very good. And to what extent do you think that life cycle assessment assesses impact on biodiversity?
Well, in fact, from the methods we use, the European environmental footprint, this method does not include the biodiversity. And for some other common methods, for example, the RESP and the CML, I didn't remember they included the biodiversity too. And for the biodiversity, I also read some reference because, in fact, one of the review from my one paper also asked me this question, and we think it's kind of complicated. There is no well-accepted method for me to analyze that, because you need to very specific data, very specific indicator to analyze the biodiversity.
Okay. Okay, very good. Then about consequential LCA. I'm much interested in consequential LCA, and I think many people are. Relative to attributional LCA, what is the main advantage in your opinion?
Okay, so for example, in the attributional LCA, because we use not commonly we use the allocation. So the allocation is mainly based on the economic value or based on the physical value, for example, the mass. But according to ISO and other agreements, that is not so scientific sometimes. So if you judge the different allocation, you might get different results. So sometimes it will totally, sometimes it's okay, but sometimes it will totally change the result. So that's the reason why I use the consequential. And for the consequential, another part is can analyze the kind of can analyze comprehensively. For example, because I created the products from the biopump, so I will, of course, the market is just this kind of size, if you assume like that. So some products will be avoided. So the emission from this product will be avoided and need to be considered. So,
okay, so you say about attributional,
yes.
The choice of the allocation method is difficult to justify scientifically.
Yes.
Okay, but if we do consequential, in the case of hemp, you say that hemp oil will substitute palm oil. Is it not a little bit the same? I mean, how do you know that it will be palm oil and not soy oil?
And in this case, that's because we consider another reference produced from the flaxseed oil. So flaxseed oil for hemp oil is kind of similar. They function. They both use for the food supplement because they are rich in the omega-3 and omega-6, as you know. So in that reference, it avoided the palm oil. That's why I choose the palm oil.
Yeah, but how do you know that it will avoid the palm oil?
In the perspective part, we will read some market report. So in the market report, we will know, for example, they will give us the market hemp oil, palm oil, fish oil, for example, and we will see the share, the trend of their share in the market. And then you will know, for example, though the amount of the hemp oil is very, very small, but it increased. The increase of the hemp oil is very high. So today is 1 kilogram per 1 kilogram needed in the market, and tomorrow will be 3 kilograms. And though maybe the palm oil is very large, it's 1 kilogram, 100 kilograms today, but tomorrow it will be like 50 kilograms tomorrow. So it's the palm oil is kind of marginal in the market. So it's less competitive compared to the hemp oil. So that's why normally we choose the marginal products in the market.
Okay. Okay. And now on to the modeling of the carbon sequestration. So I was quite surprised to see that when you did the same, you used both AMG and C2, that it gave such different results for carbon sequestration. How come?
Okay. So for the result, as you see in the, if you still remember that in the initial scene ratio on the 11, and if we have it with straw, they are very similar. One is 33 and one is 34, something like less than 1 ton per hectare. But for the other case, for example, we leave the straw on the field. Yes, it decreased a lot. The difference like 10 tons per hectare. The reason could come from a lot of parameters. For example, the AMG consider the 30 centimeter of the soil, but C2 will consider 1 meter. So of course, C2 will continue consider more salt than the AMG results. And further, there are some other mechanical result. For example, the MG, they have 2 carbon pole. One is carbon active pole, one is the carbon stable pole. So the carbon in the stable pole, it does not consider the emission from this part. So if the carbon is attributed in this pole, there is no soft loss. Well, for the C pole, it has 3 poles, and the carbon in the kind of stable pole is also considered to emit back, just because of the ratio is much lower. So, but it's still.
But which one is the best then, in your opinion?
No, there is no best. In fact, because we also think about there is different. We use another simulation tool to verify that which one result is better. Then we also think about that. How can we know the third pole is the right one? So it will be like a circle that we never get the result. And since both of these poles are already proved, they are precise by the model maker. And for example, for France, if you ask me, for France, for annual prompt, I will prefer AMG because it's specially calibrated.
Yes, but now you have shown that black locus is the best option. So how would you, if you had some more time and you would want to solve this question because it introduces a huge uncertainty, additional uncertainty.
Yes.
How would you go about it?
Yeah, for example, the reason why we choose the CPOR and black and MG, that's both of them are based on the rock C. So even though they are two different models, they are kind of based on the same formula. And if I have some more time, maybe I can try some. First, of course, if I have some more time, I can do some experiment, which maybe not so realistic. So years, but
takes a lot of time.
This is the most exactly valid way I could get my results, get the precise result. But of course, I can use some other model that specially provided for the wood, for example, the yaso or something like that. But they are not based on the same mechanism. That's why in this case we did not use that.
But you might also try to see in the literature experiments that have already been done.
Yes.
You know, because, well, to do your own experiments takes a lot of time, and there's already very many data available.
Yes. Yes. Well, that's another point, because as you see, we say that the carbon cultivation is starting in 2022, and we will analyze the stock change in the future. So even if we have the data for the past time, like we cannot say it's very reliable, because all the stocks will change with the prescription or change with the temperature, and temperature prescription in the future is obviously different than the past. So the data for the past, we can say yes, when we use this model, and this model say that our simulated data is exactly the same with the measured data, then we think this model is reliable, and we cannot say that the result in the future can tell the measured data.
That's a good point. Yes, yes. Now, you explored the potential of biopump for marginal land. What other options do exist to favor carbon sequestration on marginal lands?
Well, the other sequestration, if we do not use them in the for the biopump, of course, we could, if we only consider about the carbon sequestration, we could do something like from the agricultural method. For example, we use less tillage or plowing to less disturb the soil. So it might help us to preserve the carbon in the soil. And yeah, I think there are also other use, for example, afforestation and reforestation to change from the low productive to high productive.
Okay. And I was curious, you know, the name carbon vulnerable land, why was it chosen? What is the vulnerability?
The vulnerability is because we, as we say, we want to stop the carbon in the soil. So the initial stock level, initial carbon in the soil should be low. So it's a
yes. I would, well, I wonder why not call it, I don't know, carbon deficient land or something like that, but well, that's really a detail. And do you have any idea about the economic feasibility of the biopump concept?
Yeah, that's the way we miss that, because we in the future, if I have some time, I want to at least do something like cost analysis to let us know our biopump is feasible in the economic aspect or not. But here, because our starting point is to mitigate climate change, so we more focus on climate change part. So that's why how we choose the biopump product. Want to stop the carbon as long as possible.
But if you maybe you had some informal discussions with Laurie or Lydia or somebody else. Do you have any idea about that? If it's an attractive option economically?
In fact, why we think about that is because we consider the market of the bioproduct. So we calculated that if the product from 1 hectare of the biomass and will be expanding for the whole France, then the products we will produce more products than the products in the market now. So obviously not feasible in the economic aspect. So in this way, as we say, we may expect analyze more products, so we can analyze the various use of biopump. Maybe some of them are not so valuable in the climate change aspect, but they have more bring us more profit in the economic part. So people were motivated to do that, because if we just tell people that this plant could capture more CO2, then the farmer may not so happy to do that. So that's a lot of money, not consider about CO2. So I think that's very important to do that, even they are less valuable in the climate change.
Okay, thank you.
Okay, thank you, Ayo. So now we can move to Bernard Kurek. Please, Bernard.
Thank you, Mr. President. So first, I would like to thank Lydia and Laurie for the invitation to make some comments on your work. Very heavy work, I think. You said this, and it was very useful for me because I have also learned a lot by reading this document. And I am not a specialist, so I apologize. I don't want to disturb you, but I can ask some questions who are not really in the field that we have studied here with life cycle analysis, etc. But still, so first, of course, it's a very huge amount of work. I really appreciate how it was documented with the sources and reference and so on. It's very good, and you can find the main information if you want to have some precision in the text. Well, this is I think a very good standard of PhD document for this, and very good. Then, SAIO, I have to ask some questions. So the first one is related to the choice of IMG on C-tool. Well, I am not a specialist, I said. Okay, I agree. There is two models. Maybe one is better for France. The other one is better for everything. Maybe, I don't know. You have all the thesis. You have worked on this hypothesis. But if you test to cross the model and to recalculate some of your system, and do you go on, if yes, okay, do you go in the same direction or not?
You mean if I use this now? I use the MG for the hemp and CETO for the
yeah.
purpose in process.
Yeah.
Well, yes. At the end, when we compare the hemp with Black Lotus, so to put them in the same framework, we only use the CETO to estimate.
Okay.
Them. And for the MG for the Black Lotus, no, it's not possible because MG is especially for the annual part, so it will assume that all the residue will decompose in 1 year. So for the woody residue is not realistic, so we cannot use MG to do that.
Okay, so you have you have good scientific reason to choose this and keep this all the time for this. Okay, yeah. Then I agree fully on the methods, and sure, it's a lot of work. It's solid results and so on, but the landscape that you present, I'm not really convinced. So maybe we'll discuss a little bit on this. It's a question of choice. So if I say something, I'm not right, but you have to answer to me why you think your choice is good. Alors, the first one is the monoculture of plant is something that is not so good. And do you know why it can be a problem if you make monoculture for 100 years and 200 years maybe?
For example, for the rapeseed, obviously it's impossible that we only cultivate the rapeseed in this land and last for 100 years.
Yeah.
So it's impossible because we will meet a lot of problems, for example, the insect, the weeds, so
okay.
And the yield will decrease dramatically, so it's impossible.
Yeah.
But so as you see, that for the hemp, for example, our functional unit is 1 year happen in 1 hectare sea land. So why we simulated the shock for 100 years. That's because we want to know the influence of the shock purely from the camp. Our biopump test is only for camp here. So that's why we only take the camp as the shock chain. But when we consider generally, our functional unit is 1 year.
Yeah, but if you consider 100 years, many events can occur during this. 1 year will be good. You have a very bad climatic condition and so on. So how do you include such climatic events, disaster or something like that in the model? Could you include this in your model or not?
For the temperature and the prescription, and we can, because we use the data predicted by the data for France, and for others, for example, the disaster like earthquake or something, not really.
Yeah, but it will impact in all case all your systems. So do you think the modeling is sufficiently robust to take this into account in one moment, or would it be possible to have this or not?
From my review, the mainstream of the shock simulation, they do not provide something like that to including the disaster.
So then I have another question in this field. So monoculture, it's one choice, but okay, it gives good data, but the limits are quite present. The second one is the very long times that you take. Okay, 2050, it's tomorrow, I would say. Okay, but I just make a calculation during thesis. If I go 67 years ago, we are in the French Revolution here. I don't know what was occurring this time in China, but just imagine the situation before and know where we stand. There is a lot of change, climatic change maybe, but agricultural practice, etc. But one very important point is technology. So even if the first idea on machinery and power were still coming at this French Revolution, but there is many evolutions. So do you think it's realistic to have such simulation with agricultural impact and then a technological itinerary over this long time?
Okay, so the why the lifetime boundary is so long is not only because we involve some production there. That's because of some emission, for example, very typical emission during land feeding. It emits very long times. Every year you have some emissions. So that's the reason why the time boundary is so long. You will see that our cultivation will end at around 100 years, and after that there's no cultivation. There's only the emission during the use or because of the disposal. And for the technology way, yes, of course. For example, as one of the sensitivity cases that we consider, that French will not allow to sell the thermal, the gas drive the car anymore, so we consider the electric car after 2040. So in the future that we could predict it, we'd like to do some sensitivity analysis or directly use them to in the inventory to get more precise results.
Yeah, but still you discuss a lot on very long time, and for me it's a personal view, but I would have preferred to see just at the beginning, because we have to put the culture, in fact, so hemp in cars. It's maybe 30 years ago was the beginning to have very performant materials, I would say. Before it was tested, but not so efficient. And you can imagine that even in plants, this is also a question that I hear. How could you improve finally also the storage of carbon, just not by putting a plant 100 years in a field, even in marginal? Where are you? Where are the way to boost this carbon storage, and just not by putting hemp for 100 years, for instance? You have other solutions. So
So, for example, we consider the carbon storage not only in the soil but also in the product. So, and because it's a kind of the targets announced by the government. So, all,
okay, yeah.
Yes, we will be boosted, motivated to reach this, achieve this target. So I think that's the motivation.
Okay, yeah, but a plant, you will take one plant today, but do you think in 50 years it will be the same plant or not?
You mean after like 50 years we will still use hemp or not?
Yeah.
Yeah, that's a very good question. That's why we need to expand our biopump database so we could have.
Yeah, no, so it's not what I was expecting. But you could improve also plants. Yeah. You can also select plants, so on. Yeah. And so this is why I was thinking over a long time you can expect that technological solution can occur, of course, but also some improvement of plant, even just a plant. So to improve the take of carbon and make more biomass and adapt also the plant with the climate change, etc. So
it means some genetically modified plants, for example.
Yeah, even okay, yeah. Oh.
Okay, sorry. Yeah, that could be. But we didn't consider about that.
Yeah, I agree. Yeah, but what is your opinion? Yeah,
I think it's possible because now the genetics way is very developed. In fact, if we use that in a wild, very wild scale, I'm not very sure because the genetic plants is only, if I remember correctly, is only legal in 4 or 5 plants till now. Yeah. So in the future, I'm not sure we will use these genetically modified plants to absorb the CO2 to use for the production or not. Yeah, it's promising, but I'm not sure. Just sure.
I agree. So and to your opinion, also according to your data, you see black locust is very efficient. But there is a very strong transformation chain. So you have many products, you have a variety of products, and so on. What would be the balance between the carbon impact on the production of the plant and the carbon impact on the transformation? How could you weight the two and improve all of this? Yeah.
The balance of the carbon storage in the product.
Yeah, and then is the technosphere. Yeah.
We say that the carbon storage in the product, that's why we say carbon storage in the technosphere.
Yeah, but
it's the same thing for us. When we compare the carbon storage in the soil, another point is the carbon storage in the soil and carbon storage in the product.
Yeah, but if today there is an equilibrium, I would say, with what you are doing at the field and what you are doing in the technosphere. But to your opinion, would it be easier to improve the technical aspect of the system, so to boost the technosphere, to say, or keep the field activity relatively constant, or do you think it's the opposite that we have to do?
Well, in my opinion, I think more in the black locust, obviously the carbon storage in the technosphere will be much larger than the storage in the soil. So you could see that at the beginning, because after the cultivation, the salt in the soil will decrease. So because in our opinion, the carbon is in the soil is in 2 parts: one is active part, one is stable part. If we so little of the carbon that we include will include in the stable part last for maybe 1,000 years, maybe long. It's carbon in the active part, they will in a short time, as you may see that for the black locust, after 15 years of the cultivation, our increased salt will disappear, the salt will back to the initial value. But for the products, for example, we use that in the building, for example, where maybe the wall, so it could last much longer time than that. So we could achieve our time target, for example, we could achieve to reach the carbon neutrality before 2050, because it's just like 30 years from now.
Okay, yeah. So on the related to this, as a practical question as on methods, you at the annex, so the supplementary data, there is a complete scheme of transformation, etc. Did you discuss with the professionals, so the people making the material, on using them, on breeding, etc.?
You mean the process diagram, how I get that?
Yeah.
Yeah, most of them I get from the literature review.
Yeah, but did you try to discuss with the professional, so people making the material, people using agro-material to build a house, etc.? Did you discuss with them? It's a very
during the conference, some of them
okay.
Really like the speaker, really something like that. So we discussed them a little bit about what's a realistic situation.
Okay,
yeah. Can transfer this into the products.
Yeah. Okay. So it's not just a literature analysis. It's also so we have some experts who have say, okay, it's good or
but it's, still it's more general because every factor has their own special situation. So that's why we cannot only mold on this factor, but it's more general.
Okay. Yeah. J'ai encore du temps ou j'ai fini?
2 minutes.
2 minutes. 2 minutes. So the last question. So, alors, last one. I think I will not have last question because you have a very good answer for the question. I think it's important to just to people like us who are not specialists to be able to have concrete scheme, data, and so on. And for me, I say again, it was a very good experience to read this. And so the very last one. So will you continue in this field or not?
Yeah, I think so. So first, after that, we just have 2 cases. So further, because we planted grow the plant. So what will happen if you see some of the part of the biomass is residue? So what if we just directly transfer this residue into the products and compare to use the land, because we transfer land and generate a land use change. So we like to maybe which strategy is better to have that one or use the residue. And further, as the professor see that for the economic part, it's very important and interesting to do that. So we will know not only about it will help us in climate change, but also everything is now is kind of business, so we will know that it's feasible in the economic way or not. So people will be motivated to do that in effect. Not only I'm talking about that as a test, I really want to apply that to help our planet.
Okay, so thank you. Very good job in your case. Yeah, thank you.
Thank you, Bernard. Now we're going to hear Thibaut. If you can hear me, Thibaut, maybe you can.
Yes, I can hear you. And you?
Yes, and we can give the microphone to.
Closer to Joe.
Okay, thank you.
Okay.
Could you hear me well?
So, thank you, Mr. President. I just have to say that I'm very glad to be here in this jury on this very interesting topic and to hear about the large work you produced. For that, I warmly thank your supervisors, Ligia and Laurie, for the invitation. So thank you. And thank you for your presentation too. It was very clear and very dynamic. So I have a few questions. I think that my first question is the same as the 2 others. It's a general question about the development of these biopumps. Maybe could I reformulate differently the question, but to my mind, it's a matter of momentum between the different sectors and between the carbon content of soils and carbon content of, for example, cities. Can you tell us how you think it's possible to develop and to develop this kind of biopumps?
So you mean that how we can make our biopump strategy better in the climate change aspect, is that?
Well, it implies for me industry, agriculture, building sector. So and on the other hand, who own these marginal fields, and how can we make them use these marginal fields to develop carbon pumps, biopumps?
Okay, so I think from the aspect of carbon storage in the soils, the way we can do it better is to analyze more biopump. For example, puts the hemp in the rotation. So the hemp will not only molecular for years, we will have some extra for example, the cover crops to be planted between the two rotations of the hemp. So we'll have more carbon inputs into the soil. It will benefit the carbon storage in the soil part. And for the technosphere, I think we will use the carbon in the more, as we analyze that maybe some plants could capture more carbon, could stock the carbon for longer time and less waste the carbon during the manufacturing. So this carbon is a more ideal carbon carrier in the technosphere. And of course, with the technology developed there, our results could also be updated according to the technology.
Yeah, it was not really my question, but
sorry, could you rephrase your question again?
Oh, no problem. My question was about the feasibility of such a solution.
To use the biopump in the real life.
Yeah.
Today you give me a hectare.
Is it a matter of public policy? Is it how can we reach this aim?
Okay, so first of step is that we have this concept and then we analyze according to our model to prove that our concept really help us in the climate change and it could continually benefit us in the future. Maybe the future is a little long, but it continuously benefit us in the future. So we could do that and to the stakeholder to tell them that, oh, there is a concept and could help us in mitigating climate change. And of course, we need to compare with other methods. So will our biopump concept will be better than them or worse than them? And in fact, finally, maybe we can begin from 1 hectare, real hectare on site to do some experiment to verify the estimation I just proposed today. So I think in this way, we can gradually apply our biopump in the real life.
Okay. For example, you speak about black locust.
Yes.
Do you have an idea of the momentum of the wood sector today, and how this kind of product can be used really in the market?
It's a very good question because in fact, the main use of the wood is to produce something like furniture. But when we think that if we still use this wood to produce the furniture, that means because we also look the market report of the furniture, the main process is already furniture made by wood. So we use wood to substitute wood. It does not help us in the aspect of climate change. That's why we choose our products like the medium density fiberboard and cross laminate timber to avoid the plastic board and something else. I think this also will influence us the choice of the products in the market.
Okay, but these products could be substituted by wood products that are already in the market now.
Yes. You can use them to produce something, for example, the walls, exterior or interior wall, like with of course not only this board, but you need to mix them with like the wall thermal and concrete and so. But it's also already used in the industry now.
Okay, Thank you. Maybe we could go to the slide 9. I don't know if you can.
Yeah. Wait a minute.
Go it.
Slide 9.
It's about the choice of your candidate between all the spaces to be used as carbon pumps.
I just need to share the screen with the people here in the.
But I see it, no problem.
Yeah. Okay. So
if it's like that, there is no problem for me.
Yeah, but just to share screen for the jury here in person.
Okay. No, just about the.
Okay, you see that.
Just about the ratings you give to the different spaces.
Yes.
It's a system of points. But do you have is there some criteria that could have a higher weight than others? For example, if a plant is really invasive, we don't want to use it at all. So other ways are possible to choose the best carbon pump, or?
Yeah, yes, for example, you could see that the fourth criteria is the suitability to grow in France. And in fact, when we selecting the biopump, we found some candidates that only have the record live in Asian. So there is not suitability for Europe at all. So that's why we totally will not choose them.
Okay, so for them it's 0.
Zero.
But yes, but you okay, you put it on the side and not use it. Okay. Maybe go to the slide 16.
Okay, wait 1 minute. And you can see 16 now?
Yes, it's 16, or maybe the previous one or the next one.
Okay, sorry. This one?
No, previous, sorry.
Previous, sorry.
Yeah.
This one?
Yes, this one. Here, I don't understand if you take into account the carbon that should remain if you don't grow up carbon pumps in the area. Understand what I mean?
Okay, yes. No, in this case, we did not consider the initial vegetation on this CV land as the reference flow. It's only to have an orientation test to demonstrate that only carbon involved with our concept works or not. So there is no some initial vegetation on the CV land.
Because in marginal areas, you have carbon stock.
Yes. That's
already.
That's what we calculate in the case study, but not here.
And maybe this carbon stock will increase due to more CO2 in atmosphere, for example.
Yes. In fact, you could see that from just the case level. You will see on the bottom left, this initial vegetation, and they are calculated as a reference in the case study. Here this is just an orientation test, so we did not include that.
Okay. And let's go back to the lifespan you've made an exercise on a lifespan of 1 year and a lifespan of 100 years. Did you question some other lifespans? Because in building sector, for example, we can have lifespans like 50 years, but also lifespans of about 200 years. So did you make a sensitivity study about that?
Yes, we have the sensitivity. In fact, here you could see that from the from here, you could see that when we choose the product of the medium density fiber board is already only have lifespan 12 years, and for the cross-laminate timber, it has 50 years lifetime. So they are already, I think they already have some difference between these two products. But for example, the CLT it could be used for 50 years or used for like 200 years. We didn't consider about that. So.
Because in building sector, we use generally 50 years.
Yes, more general.
I do not really agree with this lifespan, but it's the norm.
Yes, that's a common lifespan.
So if we did that, how are your results compared with the results at 100 years of lifespan? How do they change?
You mean if I consider here as 200 years, what will happen?
Yeah.
Yeah, and then of course the current storage in the product in the technical sphere will be much longer. So if we have a look of the final result, the dynamic result here. So here, sorry, maybe you cannot see, so I'll point it on the here. Where's my cursor? Yeah, but maybe. Okay, so you can see that here at the end of cultivation, the negative emission is continuously decreasing. But if we have much longer lifespan, for example, 200 years, here will be more flux. Maybe we'll emit it as the it's just after 100 years like that, but our time boundary definitely will be much longer than this monitor.
Okay. My last question maybe is about the different ways you use to make your life cycle assessments. You use a dynamic one,
yes,
and static.
Mm-hmm.
In static, there are lots of different impacts, and in dynamic, it was just about the greenhouse gases,
yes,
and climate change. How could you make a synthesis of these two kinds of assessments? And for you, what are the strengths and the weakness of dynamic LCA?
Okay, could you repeat the first question again? I did not hear clearly.
The first question was about how to make bridges and synthesis between the dynamic and static LCA.
Okay, thank you. So for the relationship between the dynamic and static LCA is that first we need to do the static LCA, and then we could use the inventory from static LCA, and then we collect the more inventory about the time, so we could build the dynamic then. So it's like first we do LCA, it's static, and then we could do the dynamic way. And for the dynamic way, of course, the shortage is that there is still, we only can use for the climate change. So for the other impacts, for example, in the static, we have 17 in total, the environmental impacts, but in dynamic, we only have one. So we cannot know if there is any trade-off in other environmental impacts in the future or not.
Okay, thank you for your answers, and thank you, Mr. President. Okay, for me.
Thank you very much, Thibaut.
Okay, so now it's time for me to ask a few questions before your supervisors. Okay, thank you. Obviously, I would like to say thank you for this nice presentation, and I should say that I have learned a lot with your PhD thesis manuscript. It's a very well written document, and I really appreciate it. I would like to also thank your supervisor to invite me to the jury, because it takes time to do that, but at the same time we learn a lot. So I'm really pleased to do that. Well, some of my questions were discussed before, but I would like to come back to this question of regarding long-term simulation. Maybe it's a simple question, but in your scenario, in your simulations, how did you consider the global warming itself on your scenarios? You mean you simulate for 1 year of future tendencies? What was the assumptions for the global warming itself, and how this influence your result and your scenario?
Okay. Okay. So as you see, that the temperature will keep increasing in the future. So that's why during the simulation, especially in the simulation, so we use the RCP 4.5. It's like we will increase 4.5 in the future, and also if just for fun, we try for 8.5. So the result will differ a lot.
Yes.
Yeah.
Okay.
Because the temperature is well higher and higher, so the result will change.
So the scenario is, how do you define this scenario? Is it a scenario business as usual, and we continue to use fossil energy and temperature increase to 4 degrees? Is that the main assumption of this scenario?
Or directly pick the scenario from the 4.5.
4.5.
Yeah, the future will increase 4.5.
Okay. Okay. So this is more or less business as usual.
Yeah.
Okay. What are the consequences, especially in the areas that you consider? You consider the south of France. Most of your, in the French area, you show us these zones. Okay. So you have 2 scenarios. In which case did you make your simulation? For the second one, for all that zones?
So here the difference is that here we don't have the intensive grassland because we don't know exactly the use of it. And here we include the intensive grassland here. So when we did the further result, we used this one to have the proportional difference with this shape.
Yeah. Okay. I see. And if you see the south of France, as you can imagine, if there is an increase of 4 degrees in general, this south of France will be especially influenced and highly impacted by this global warming. I was thinking about water. Did you consider the water availability, the rain events, and the difference in the water availability in these zones in your scenario? Are they considered in your simulation?
Yeah, in the simulation, we consider the prescription and the evapotranspiration.
Yeah.
So it's also provided directly from the predicted data of how much prescription will be in the future.
Okay, okay, and I think it. And what can we consider any irrigation method for hemp, for example? Because I know that in the south of France, more and more we will consider irrigation for different kind of cultivation, not only the more difficult type of crops. So did you consider any scenario with irrigation? Does it make sense?
Yes, we consider irrigation in the hemp simulation because at the very end of the model, the irrigation and prescription, they are all water, so they all will be merged together and that factors into that.
Okay.
So, yeah, we consider them.
And did this option influence the eutrophication in any sense?
No, not in the eutrophication, but only in the current change in the soil.
Yes, but as you talk about eutrophication, I was thinking about that specific impact. Can you explain in which ways different scenarios impact eutrophication? Can you remind us?
Yeah, for the eutrophication, it's more like the fertilizer use.
Yes.
Not in for the irrigation. Fertilizer use impact is much higher, and for the freshwater eutrophication, it's mainly depends on the phosphate use, and for the marine use, it's the nitrogen.
Yeah. Okay. So, in general, do you think that type of biopump option will encourage good agriculture practice? For example, you talk about use of fertilizer, but I think also they can use pesticides or whatever. So do you think these biopump options will encourage good practice or maybe bad practice?
So that's also one of the criteria that when we're selecting a biopump, so the agricultural intensity, we do not want this kind of biopump will require a lot of, for example, the nitrogen fertilizer because it will emit H2O directly into the climate change.
Sure.
And for the pesticide and you control the pest and weed, we want to do that. But for marginal, we may not be able to have so many labor to do that. Not one of our criteria is that we want this kind of plants to tolerate various of impacts on the environment. So we can sacrifice part of the year so to get less intensive agricultural management.
Okay, thank you. Different question. When you consider the black locust option, so you cultivate trees, what is the frequency you consider for harvesting the trees? Is it after 35 years that you cut the trees?
Yes.
Okay. Did you consider a range of time or any sensitivity analysis on that specific?
The reason why we change 35 years is because 35 years because the root growth rate would grow mature at around 35 years. So if we start at 35 years, after that, the growth rate is very low.
Okay.
It means the carbon capture is almost zero or very low. So it's not our favorite as we want to capture more CO2. So, and lower, obviously, it's not very, if we just consider 1 or 2 years, it's not very sensitive because it's 35 years and our dynamic time boundary is very long. So 1 or 2 years is not so interesting, but if we consider longer, for example, we cultivated the black locust for 90 years. It's record that it's grown for such a long time. But from the 35 to the 90, it will stop capture CO2. So it's less meaningful to be a biopump.
Yeah.
To amplify to maximize.
Okay, 35 seems to be a kind of compromise, which makes sense. But if we choose 20 years instead of 35, because you talk about more than 35, but maybe less than 35 will be interesting if the growth rate is better during the first 20 years.
Okay. If that's so, I would say that maybe we could cut it at the after 20 or maybe 25 or 30, because at this time, the growth rate is the most high at this time. So the carbon capture is the, we can capture most carbon during this time. For example, if you just cultivate 10 years and cut them, no, because the growth rate is very low. And maybe the carbon capture from year 0 to 10 is even less than the carbon capture from 10 to 15. So if you say that, I would recommend to maybe a little bit lesser, but I think 35 is very.
Okay, I'm asking this question also because maybe you don't know, but at the moment, for the problem of big storms and weather disturbance, sometimes people are more encouraged to cut rapidly these trees to not have a risk of a storm with everything damaged. So sometimes the insurance encourage also people to not wait for 35 years because it's too long. You have high risk of seeing something, an event which destroy your product at the end. So that's also something to think. Well, if I go to the uncertainties, because obviously you have a lot of uncertainties, but you know that. You know that, and you did this sensitivity analysis, etc. So as a conclusion, if you have to defend your work, where do you see the biggest uncertainties? And if we have to do more research to make your approach more robust, in which side do we need to work?
Okay, so the not the uncertainty from here, but the uncertainty of my work.
Yes,
okay,
global.
So as you see, that the difference of the simulation model, they will use high amount of uncertainty because how soil is one important pore in our system. So I would say this is one kind, and the other kind is the we analyze results for the future. For example, we don't know because we use consequence one, so we want to know what is the exact consequence data in the future. For example, the electricity use and the heat use. But it's very
kind of the original for France, for China, obviously are different. And this kind of data sometimes we are not able to obtain. So I think it will also generate some uncertainty. And further, because some now it's globalized, is the error. So some work will be done in the other countries. So and some work will be done in the France or Europe. For example, for the agricultural part, obviously they will be done at the France. And the influence of the region sometimes is very high. Again, I will say an example of the electricity in China and France, and the influence are very different. In France, maybe if we use the nuclear mode, so influence will be in the respiration organic, in the China maybe because we use a lot of coal, so climate change will be higher.
That's a good okay. That's a good transition for my next question, because I would like to ask you, as you have used this French model, and maybe you can imagine doing such kind of work in China, maybe. How different would it be if you have to consider China instead of France to do this kind of work? Do you think it makes sense to do it for China? Or do you think things are strongly different, or can you use directly the same kind of approach by adapting the inventory? But what will be the adaptations that you need to do?
Okay, so first, the framework, like the way how we do that could be an experiment, how we choose the model, how we select the inventory. But for example, the first step is the city land that we could convert it. They are different because the land, the stock, and the different land cover type are all very different. I saw also some reference in China. They also very so the first step, the reference for will be different. And then the product type also will be different. You see, the one of the criteria is the biopump should be in France. So some of them could live in France, but some of them could not be in China. And also some low power need to be considered. For example, the use of hemp maybe suitability. And the product costs, some products are more favorable for the European market, some of them are more favorable in the Chinese market, and we can produce a lot of products domestically, not like France. Maybe some of them will be transferred to the other parts to manufacturing, so the efficiency of the transportation need to be changed.
Okay, okay. Last question. Your work was done in the framework of MOPGA program. So did you compare your scenarios, your result to other people working in the MOPGA program? And if you have to define your options, your scenarios with your colleagues, what will be the main argument? And maybe if you have one or two important numbers to keep in mind to convince people that this option is good compared to another, which can be completely different. What can you say about that?
Well, for me, because I'm the guy who work on this conversion of the planting biopump on CV land, I sense I use more about directly use the residue part for transform the residue to pyrolyze to get oil, for example, to
proteins.
Yeah, and protein to get food. But this is more like I have a lot of residue here, and I think this will be very good basement for them to do the work. On the field to be generated.
Okay. Okay. And can you say one number which can be keep in mind to summarize one important message? I was thinking about the potential of your approach. I remember during one of the first chapter, you indicate maybe the maximum potential of this biopump. Can you say one word about that? One important numbers to keep in mind.
Okay, if you say that if we grow the biopump on the free land and we convert in the most
optimistic
situation,
yeah,
that we transfer all the carbon into the product, and product is longer than 100 years, for example. But anyhow, it's all of the time boundaries that we consider that we could compensate around 13% of the CO2 budget, only CO2 budget in France every year.
13%.
Yeah, it's very high.
Which is quite significant.
Yeah, it's very high because we convert all the carbon in the
the technosphere, and also we consider the carbon structure.
Okay, so let's finish with this optimistic number. Okay, now I have to say nothing. I am Ligia to make a word about the work. Yes, Ligia, please.
So we are close to the end. Thank you, first of all, the members of the jury to participate and to examine this work and to make very useful comments for us to improve our vision, the certainty of our results. And now, I don't know if I already did it, but thank you, Laurie. Thank you, Laurie, for your collaboration. First of all, I have to thank Laurie because we built this subject together, and it was an interesting adventure for both, for all three, for us. And from a scientific point of view, and I found that we have complementary approaches and visions, and it was very helpful to develop this work. Yeah. Even if it was sometimes laborious and hard to work all together, but finally, yes, we succeed. So this is our first common thesis, defense in TBI, and it's very nice. So I'm very happy for that, and I think that we will drink some champagne after that. So maybe tomorrow. Now for Zhou, some words. Yeah, I remember the day you come in INSA. The first day you arrived here. It was sometimes it was quite difficult, but with the time, I found that you improved your approach to the thesis work, and you made really a great progress until the end, and I congratulate you for that. I want to tell you that you are a hard worker. Yeah, I think that you work a lot, and you have stuck to the thesis subject also, and to the requirements of this scientific work, which is not easy for all people. So this thesis may have caused you some stress, maybe, but the result is there and it is nice. So I hope that you learned something here, that this day was beneficial for you. Yes, I hope. And that it will help you for your professional project and future. Yeah. And I hope also that if you come back to China, you will promote the scientific work for the environment globally, yeah, for climate change especially. So congratulations.
Okay, thank you, Ligia. Now to conclude. Laurie, please.
I don't know.
Yes.
What to say? Well, the same thing. Huh? Thanks, Ligia, for this collaboration. So we know that sometimes it was not always easy for Zhou. One say one thing on consequential SCA, one say another thing. But as Ligia said, at the end, all of that became nicely put together, and you got the best of all. So yes, I'm also very happy of the result. Just the same as Ligia said, I really appreciated to see your hard work, and generally we're very positive all the time and enthusiastic. So I really enjoyed also your sense of humor all the way through. You made me laugh a lot. So And then to rebound a little bit on what Mathieu said, if you should meet Macron tomorrow, based on your work, what would you tell him to do?
I would tell him that he should try to give me 1 hectare of land.
I would say that again. You would tell him to give you 1 hectare of land, and then
1 hectare of land, so we could really apply maybe half of them is half and half of them is close.
As I said, I appreciate your sense of humor. But if you should tell, if you should summarize your impact to science, so in a few keywords about your finding, if you should explain it, for example, to your parents in China, what would you say? What are the key findings of this work?
The finding of this work is that we have this concept, and this concept will really help us to achieve the climate change, the climate target that we set for, so we can really help us on the not only France, but also in China, the whole world to maybe less suffer from climate change.
Okay, so that this concept exists, but there is need to further validate.
Yeah, of course, I would say we
can. Good. I think that's it from my end.
Okay. Well, I would like to ask you a last question because I'm curious about that point. But at the end, if you have something to say to Macron or whoever, someone, don't you think that one message could be, okay, we need to make as much as possible things, materials in construction, for car, for anything, for isolation with biomass, with wood, but not only black locust and not only with that biopump zones that you identify, but is it a conclusion also of your work? Make anything that we can with biomass. Does it make sense or not?
No,
totally?
I don't think so. But in
Why?
respect of the climate change, and since we have the result, if you ask me how to solve, how to deal with the climate change, I will recommend you use the biopump.
Yes, but maybe you don't see what I mean. I mean, biopump, your concept of biopumping is you use a specific land with a specific type of vegetables to make specific products. But at the end, the main impact in your result is due to the immobilization of the biomass of the organic carbon into materials.
Yes.
That's the main impact.
Yes.
So if we agree on that, we can say, okay, if we can, with any vegetable materials, we need to catalyze and to mobilize this vegetable material to make anything.
So also some products, because of the for example, the bio-based products, sometimes they cannot meet the strength requirement of the use of the material, so they cannot use at that time.
Obviously.
Yeah, but if we have the possibility to reply that and it will reach all the requirements that we need, then I will review. Yes.
Okay. Thank you very much. So this is the end of the discussion. It was very nice. So now we need to have a specific time with the jury before coming back to you. Okay?
We will stay here for
okay. Ouais. On est obligé d'applaudir. Sympathique.
So I will close here, and then we can connect again on the other link. Thank you all for attending.
Okay.
I will reopen it again when we give the results.